Okay, this was very abstract, and if you're feeling a little lost with this, I completely understand. Let's bring it back home in a real-world example. Before we do that one, I'd like to actually look at this one. So here are your steps for computing differentials. They're very similar to our steps for computing the linear approximation. So I'll let you pause the video and read through that. And then when you're done, we're going to go ahead and apply those steps to a problem that we've already visited. Okay, so we want to use differentials now to approximate the fifth root of 33. So just like when we were doing linear approximation, we need to come up with a function that approximates the operation that we're trying to do. So our function will be the fifth root of x. We again need to choose an anchor point, just as before. Okay, so let's again, like we did in the last problem, let's pick a equals 32. Why? Because 32 is close to 33, and 32 is easy to evaluate in this function. Okay? So now what we're going to do is we're going to calculate differential y. Okay? Well, differential y is equal to f prime of x differential x. Okay? Okay, so let's go ahead and do this computation. So we need to know what f prime of x is. Well, f prime of x as a function is the fifth root of, oh, sorry, that's not the derivative. F of x is the fifth root of x, which we could write as x to the 1/5 power. So f prime of x is 1/5 x to the minus 4/5, or if you like, just as we did in the last example, we could say that's 1/5 times the fifth root of x, all raised to the 4th power. So we're now going to evaluate this at the anchor point of 32. So f prime of 32 is equal to 5 times the fifth root of 32 to the 4th power, which is equal to 1 over 5 times 2 to the 4th, which is 1 over 80. Okay. So now we get that differential y is equal to 1 over 80 times differential x, which differential x stands for our small change in the x value. Well, in this case, differential x is always the same as delta x. Okay, that might be a little bit confusing. Let's return to the previous picture that we were just visiting at. Notice that here, delta x stands for the change in the x coordinate from the point that we started with, our anchor point, to the new point. Differential x stands for the change in the x coordinate from our anchor point to the point on the tangent line. And so delta x and differential x are the same. Okay. So delta x, though, is the change in the x values. Well, we started off with the x value well, we ended up at the x value of 33, and we started off at the x value of 32. So our delta x in this case is 1. So this is what we're going to multiply f prime of x by. So we get that differential y is equal to 1 over 80. Okay. If you're paying attention, if you're comparing this example that we're doing to what we did when we computed it as a linear approximation, you see that all of the same components are there. It's just a different lens to view this with. Okay. So instead of actually getting an approximation of the function right away, all we get is the change, the approximate change in the function. Okay. Finally, we make the last statement, which says that f of 33 is equal to f of 32 plus 1, but that is approximately f of 32 plus differential y. So then if I want to know what f of 33 is, we have f of 33 is f of 32, excuse me, I should say approximately f of 32 plus 1 over 80. So that f of 33 is approximately 2 plus 1 over 80, which is approximately, well, this equals, these two should be equalities. This equals, that'd be 160 over 2 plus 160 over 80 plus 1 over 80 which is equal to 161 over 80. So this is what we're using to approximate f of 33. Notice this is the same answer we got when we treated this as a linearization.